is a talk on how we get from where we start to where we'll be. That's pretty general. But, come in. Hasn't started yet. Just doing a preamble.
Preamble.
Okay. So, my name is Pooley. I am an honor student in computer mathematics. My honors research is in the field called algebraic geometry. This talk is unrelated to that. It's on an area in physics. By the way, is this interfering with if I have all the lights on? I just want to be able to write the words so you can see it. Can you guys do this?
Yeah, we're good.
Okay, good. Okay, so this talk is on an area in physics that we come across in second year, I think mainly for most people, on this way representing these quantum systems called qubits. And they're typically shown in this nice neat picture on this sphere called the Bloch sphere. And when you first learn this in quantum mechanics, it's kind of taken as a just take this and use it. Don't ask where it came from, unless you think you want to get crazy. But this is more so. This talk is an ode to the wanting to learn the mathematics behind the Bloch sphere. So, if you haven't done physics, this will introduce you to some things in intro to quantum mechanics, and if you have, this will probably bridge some of the mathematics you've seen in the later units you've done. Or I hope there's something for everyone in this talk. Can I actually quickly get a show of hands of who's done maybe first year physics? Okay. Can I see second year physics people? Okay. And third year physics? Okay, just as many as the second year physics. That's great. Okay. And also seems like a lot of the casual academics that we sit here. But if you guys are here, then who's flying the plane? Okay, so let's get started, shall we?
The administration reckons that autopilots are not.
Come in. This is sums. Okay. So this is not working. Okay, it's working. Yeah, so the structure of this talk is going to be, we're going to look at qubits and spin from a historical perspective to see how it connects to the Bloch sphere, and we're going to then dive into some of the mathematics behind this, namely the topology underlying this, the state space mathematics, and an object called fiber bundles. That's kind of, we'll see that paves the road for a lot of what we'll be doing. And the main object of interest, the car to the road, if you will, is the Hopf vibration, and that is the mapping that links between kind of this ambient area where we're beginning to the Bloch sphere, which is a solid destination. So this is the Hopf vibration, is the mapping that will take us there. Okay, so what is the Bloch sphere? As I was hinting at earlier, it's this nice representation of qubits. The surface of the two spheres, which is this sphere, has encoded on its surface the states that a particle could be in. And I'll dive into more so what the states are in a second. But just know that this sphere nicely captures the geometry of a lot of what's happening with qubits. Mainly, the main thing here is that antipodal points, so points that are opposite poles to one another, represent orthogonal states. So what that just means is they have no overlap. So if I measure this, you're not going to get that, or there's no mutuality there. Okay, so let's look at it from a historical perspective. A bit of history. Do you like what I did there? A bit. Okay, so bit of history. We start off with the famous experiment in 1921, conceived by Otto Stern, where you fire these silver atoms out of this silver atom gun, and it passes through. And so here's the gun. I should probably label these. So one is the gun. A string of these silver atoms pass through this magnet. So it's an inhomogeneous magnet, and you have a screen on the other side that measures the deflection of these silver atoms as they pass through there. And a year later, after it was conceived, Walter Gerlach conducted that experiment, and there were some noteworthy results because until then they had this framework of physics. We call that retroactively classical physics. And classical physics tells us that what they were expecting was that the silver atoms in the magnetic field would deflect in a continuous manner. So we'll talk about what angular momentum is in a second. But the angular momentum is related to the magnetic dipole of the atoms. And when it hits the screen, it should indicate that the magnetic dipole is taking, hey guys, come on. Oh my gosh, you guys are awesome. But there's going to be this continuous deflection of these silver atoms that appear on the screen. But as we've seen in many parts of life, fact is stranger than fiction. So what spin is we should talk about angular momentum. So this is my spin interlude. We have a particle. The wisdom at the time was that if you have something rotating around another thing, you can take, it's the common right-hand rule of you have angular momentum, and you have the axis of rotation, and you have this momentum of the thing that's spinning. And you get this third vector with the cross products, and it's angular momentum. And this should be a continuous thing. So the wisdom at the time was that if you have these particles rotating around the atom, they should have this continuous array of magnetic moments. And for some reason, they were only seeing, going back, they were only seeing two splotches of silver atoms. So they weren't seeing a continuous thing, they were seeing it taking one set of values and another set of values. So it seemed that angular momentum was discrete. And working off that with the discretized angular momentum, we can label that mathematically, these two values, as spin up and spin down, maybe motivated by whether it was deflected upwards or downwards through the magnetic field. But we're going to use something called Bra-Ket notation, which is common in physics, which is basically this right angle and left angle bracket. So these are both wrangles. Yes, so we have these two independent states, and mathematically we're going to treat these as independent basis vectors. So in linear algebra, we're going to think of them as having a dot product of 0. So they're perpendicular to each other, if you like. Because physically, when it went through the magnetic field, it was either going up or down. There was no in between. So these kind of represent one or the other, or this binary states that it could occupy. So because these form our basis, I should probably say that we can scale these, I'm going to call them vectors. We can scale these vectors by elements in the complex numbers, because the extended Stern-Gerlach experiment would allow for interference when you measure in multiple axes. So interference is more easily captured by complex representation that you recall from first year maths. You can represent a complex number using like e to the I theta times something. And to capture the phase effects of these multiple interferences, it's easier if you think of them using complex numbers. I mean, you could devise something probably with reals, but it would probably be more complicated. Right? So we'll use alpha and beta in C to scale this. And these two vectors, in a way, one sec. Okay, so these two vectors span what is our state space, and that is C2. And the columns, you can think of elements in C2 as these columns alpha, beta. And we commonly write that as ket of psi, and these form what are called spinors in the state space C2. Okay, so out of interest of probability theory, we want to normalize these spinors because we want, let me write it out here. So we have some state psi, which is some linear combination of alpha spin up plus beta spin down. This is some state. And we want this property that the sum of the absolute values is equal to 1. This is, out of probability reasons, we want this to represent the probability of spin up occurring, and this to represent the probability of spin down occurring. And so the sum of these two probabilities should come to 1. So in a way, the length of this should be 1 in order to do that, because spinors exist in C2, they can be any length. We just normalize that. So we're just taking the norm and we're dividing that. We're dividing the whole the original vector by that. So now we have this new, modified space that is the original spinors, but normalized, suggestively. Where should I be putting this thing? Like this. Okay, I should probably mention before that our state space C2 is isomorphic to R4 as vector spaces. In English, that just means you can think of the complex numbers as just like 2 copies of the reals. So, in a way, if you have 2 copies, you have 4. Big, that's awesome. So now, the reason why I did this is because we want to be able to interpret the normalized spinors. So geometrically, the normalized spinors, you have these objects that have unit length in 4 dimensions. From this, we have what essentially is like a ball in 4 dimensions, and we call that a hypersphere. It's a sphere whose the surface is a 3-dimensional thing, and it exists in a 4-dimensional space, and we denote that hypersphere as S3 existing in R4. Okay. This thing on? Oh yes, and suggestively we'll call these normalized, the objects contained in this, so this just means in. So we have some psi in this hypersphere. We're just going to call these the normalized spinors. So if that makes sense. Things in here are normalized. Now here, the spinors are now normalized. Okie dokie.
I think the mark would point it up.
Up?
Yeah, I
Holy.
noticed it.
Okay. Thank you. Okay, so now we're in S3. That's awesome. But we have some coordinate redundancy, we'll see. Our normalized spinors, they're not perfect yet, and we'll see why in a sec. Come on, oops. Okay, so normalized spinors can have the same norm squared as others. So if you have 2 spinors here, psi, and it's related to phi by some phase term, I theta, where theta is some like real number, and that kind of represents the circle. In a way, a circle has unit length 1, so it doesn't change the modulus in a way. And I say that there. It doesn't change the modulus of this. So in effect, when you take the norm square of this with the inner product, by this relation, the phases cancel, and you have the inner product, you have the norm square of phi. And this is kind of redundant. This captures some essence of non-physicality in the system because the spinners were a real thing. The silver atoms, I mean, that thing there was not like in the information of the silver atoms. So you want some way to remove the fanfare and be left with the physical object. And this talk is gearing towards a way of removing the non-physical aspect of these spinners. So we set up an equivalence class, and what that just means is we have two objects, and we'll call them related, or we'll call them in the same equivalence class if they follow some relation. So namely, this just denotes that some spinner is related to the other if they are just multiplied by some phase factor into that data. So we're going to group those elements together. And the idea of this is that in one fell swoop, we want to be able to remove and condense all of the objects that are different by a phase into a new class, a new system that doesn't have this redundancy. And to do that, in mathematics we call that quotienting. So we'll need an object that captures all of these phase terms, and the object that does the job is a group called the unitary group of dimension 1. And all this just means is that take elements in the complex numbers with length 1. And if you recall, that's just like e to I theta in C. That just, if you want to see that kind of more, this is like, everything here is like, this is the unit disk. Everything lying along this circle is length 1 in C. So these are precisely the elements e to that theta. So this is a group. It follows the group axioms. Let's first, I'm going to give you guys some back pocket knowledge. So if I speak, it doesn't really make sense right now. Just put it in your back pocket. Let it sit around in there, and we'll pull it out later. So I have here a train tracks meeting for what is projective space. Because I'll create an analogy. Imagine you have two parallel train tracks, and they stay parallel in Euclidean space, but as they go to infinity, you can imagine that the parallel lines meet at some point infinity. So that's the rough idea of what projective space is. You have parallel lines meeting, and more rigorously, we want, this is going back to equivalence classes. We say 2 points are similar in, let me grab an eraser. Okay, so we say 2 points x and y are similar if x is equal to y times some lambda. And lambda can be anything in the field. So we're identifying objects that are just scalar multiples apart. In a way, you can think of that if we think of like R2, for instance. This is R2. Lines that run through the origin, that's not, imagine the origin. That's the origin. All the points along this line are just scaled versions of each other. So we condense that to 1 point. So like say x is here, y is here. That just falls into the same equivalence class of some thing, and we represent that using ratio of two things. Here, let's say this is 1, no, 2. So this is 1, 2. In projection coordinates, the individual coordinates aren't well defined, but the ratios are, so that's what this colon means. So this could also, the representative of this could be 1, 1 and 2. So basically, and this is true for any line that runs through the origin in any way. So we just condense them all into these things and just put it in your back pocket and don't think about it right in the meantime. We're going to move on to the road ahead. S2, eyes on the prize, guys. To go far, S2 seems like it's a little bit of a distance away. We're in S3 at the moment. S2, we want to get there. In order to get there, we need to see the road ahead. So I put here a quote: "To go far, we must see far." Oh yeah, that was Okay, so in order to see the road, first we need to see the first step, and we need to learn what a topological space is. And this is more like a 30-second explanation of what a topological space is, because I didn't think to explain it to somebody. But you have some set X, and you have some notion of open sets on this larger set X, and the collection of all those open sets on the larger set forms what we call a topology. And when we group the open sets, the collection of open sets, which is tau, with that parent set, we call this a topological space. And so now we're ready to see the road. So that road is provided to us by what are called fiber bundles. So we have 3 topological spaces, E, B, and F. And we'll call E our total space, B our base space, and F the fiber. And we'll see why this is relevant in a second. And then specifically here, a mapping from the total space, E, to B is, we'll call it pi. And that's the projection of the fiber. So, and altogether these things form a fiber bundle. We'll see the desired fiber bundle of interest is this one here, S3, S2, pi, and S1. We'll come to know that phi here is called the Hopf vibration, which I mentioned in the intro. And we'll construct the mapping from S3, where we're currently, right now, we're in S3, but we want to go to S2. So, me jumping was pi.
Wait. In that bracket, where you've got S3, S2, S1, which one is E, F, and B?
Oh, thanks for asking. My bad. So our total space is where we're currently in at the moment. That's S3. Our target space, which is the Bloch sphere, which is S2, that nice sphere representation. And S1 is the fiber. So that's F in the previous example. And why I say S1 is the fiber is because, in a way, S3 encodes on its surface these fibers S1. And remember how let me put this up. Okay, so S1 is identified with the unit disk, like this. Remember, recall that the elements of this were of the form e to the I theta. So I'm just going to use that symbol. Doesn't mean anything other than just some relationship. So we need to get rid of this information e to the I theta that's encoded on the surface of the free sphere. And in a way, the mapping pi is removing that in a careful way, and we'll have to see why we need to be a little bit more surgical with this mapping. So we'll first have to look at a property of fiber bundles. Like this is just like a property of fiber bundles that are important is called local triviality. And to put simply, it just means that open sets in the total space, which is S3 for us, look like open sets in the product space. And what the product space is some, I should have mentioned here, but the product space is the base space Cartesian product with the fiber. So these are the topological spaces. And we'll say that some neighborhood of the total space is neighborhood B is homeomorphic to neighborhood U in the common space. Sorry, it's not that neat, but it's neat. But anyway. So let's connect this to the specific example we're working with. So the product space here is S2 cross S1. So we're kind of creating like an analog for the three sphere, where S2 is kind of like the target, and I like to think of this Cartesian product as like simulating that information that was on the surface of S3. And open sets in S2 are have these open sets U cross S1 in the product space. So that's just the product topology. And all together, these form a commutative diagram. So this is the open set in the total space. It can get, via the Hopf regression, mapped to an open set in the base space. That's the way we want to do, because it's the short way. But there's an alternate valid name other way, utilizing the homeomorphism to an open set here. And just because this is a product, Cartesian product, we can just project to the first factor, to U. So homeomorphism to projection is the same as just doing the surgical mapping pi to the open set in the base space. And we'll see why these paths aren't the same. It has to do with what the circles are doing. So the circles in S3 are, in a way, fundamentally different than the circles in the product space S2 cross S1. And for this, I kind of want to get volunteers. Can I get maybe 4 people to come down here with me? Yeah, 1 person. Another person. Wait. Okay, fine. Okay. So I have 4 people. Oh. Okay, yeah, more than Mary, come in. We'll okay. So still need 1 more. Come on. Okay. Do that. What is your name?
My name is Archie.
Okay, this is Archie. Your name?
Max.
Max.
Albert.
Albert.
Julius.
Julius. This is not a microphone. Okay, guys. Can I ask you to stand here, please? Okay. These are my lovely, lovely volunteers. I didn't have to select anyone. This is not a Hunger Games. Okay, so these guys will be my circles. They'll show what the fibers are doing. And so we need to think of these circles. I'll tell you guys what to do in a sec. Circles, these circles can link. Just like, if you imagine like circles just interlock like this. So the simplest kind of link is called a Hopf link. And that's just where they overlap. Or they interlock once, as opposed to multiple times. Okay, so I'm going to need 2 of you to Hopf link and demonstrate. So you 2 do it. This is a Hopf link. Okay, and one sec. Every circle on the surface of S3 is Hopf linked to every other circle exactly once. So to illustrate this, I'm going to have, what was your name? Albert. I want you to link with these 2. So, okay, I'll direct your hands. So, yes, beautiful. So you stand like this. So this is 3 mutually Hopf-linked circles. Joules. Enter this. Okay, you need to be. Oh, be careful, guys. Okay. Ta-da! Round of applause. Okay, thank you guys. Unlink. Stand here. Now, we're gonna see the difference to where's my microphone? Here. Okay, so we're gonna see what that's what S3 was doing, what those guys were doing. So S2, the product space, S2 cross S1, are not linked and they do not intersect. So guys, hands like this. This is what S2 cross S1 is doing. It is not linked. Come on. This is what the product topology is doing. It is not linked. You guys are not linked. Thank you. Round of applause. Okay. Because those guys weren't linked in the product space, you don't have to untangle them in a way. They can kind of just like, if you think of this Earth as S2, then those guys would just collapse under projection, right? They don't interlock with each other in order to, and they don't have to worry about bumping shoulders when they want to collapse to the larger S2, which is our planet. And that's the problem. They were problematic. So, one second. I want to capture this better using a really nice visualization by a person named Nico Belmonte. Okay.
No spoilers.
Let me refresh this.
You might want to turn the front lights off.
Oh, okay. Let me put some mood lighting on. Okay, guys, things are getting serious now. Okay, so it's looking like it actually might run 15 minutes, but that's just, where's that gonna go? So this is in a way, you can think of this circle here as one of the circles on the surface of S2. On S3, the hypersphere. And what we're seeing is a projection of this circle from S3 down to into our, it might run a little longer. So we're gonna now start accumulating points on S3, and we're gonna see that their projections into our 3-dimensional space are all Hopf-linked with each other. And you can go interact with this on, because this is free. You just go on the website. And I'm trying to scroll this thing. Okay, so here, this is a really nice angle. You can actually verify this yourself, but every circle is linked with every other circle. So if we only had 2, it would look like this, a Hopf link. But now we have n number, and they're all doing this. So you can have a look at another. So this is like a discrete great circle of S3. Don't need to be scared what that means. So now we're changing the latitude of S3, and we're seeing how these circles behave. And now we're increasing the number of cross sections, or discrete cross sections. And we can see no matter where we are on S3, they're all Hopf-linked. They're all doing the same thing that these guys are doing. Okay, let's proceed. These things are not the same. They were not the same thing. Those, when they were doing this, that was not the same as when they were linked. Okay. So now, going back to the mapping, we took a bit of an interlude there. Let me turn off the mood lighting. Okay. Oh, yeah. So, to quotient S3, that was the idea of removing these base terms, we need to identify it in a group, because for me at least, it's hard to imagine what it means to quotient S3 by U1. So, to identify S3 with a group, the group for that is called SU2. These are basically 2 by 2 matrices that are unitary, that's all that means. And they have determinant 1. So you just take that product again. Determinant 1. And you might, the acute observer will realize that this determinant condition being equal to 1 is, did I write that out? Remember I wrote this, guys? Remember I wrote this?
Yeah.
This is what happens if you take the determinant of an SU2 matrix. Now that should be like, whoa. So like, yeah, the determinant is analogous to that previous condition of normalization. And so we can establish that connection between elements of this to the normalized spinors in S3. And it's easy enough to construct that bijection by just looking at the first column. That determinant condition of being equal to 1, is the same as just the first column of the SU2 matrix. And it inherits these properties of being a smooth manifold. That isn't as important as what comes next. So we take the quotient SU2, quotient by U1. And I tell you that this is S2, but I want you to believe me, because how do we know this removes the fibers, this is S2. So I'm gonna need you to reach out of your back pocket, remember that projective space stuff, because we want to be able to identify S2 with that quotient. In order to do that, the bridging tool we'll use is the complex projective line, or CP1. So CP1 is pretty good in this case, because there's an object called the Riemann sphere. So a short summary of what the Riemann sphere is if you imagine taking the complex plane and trying to ball it up, you're missing a point. That missing point can be filled in by something we call the point at infinity. And to more easily identify this with the complex projective line, allow me to demonstrate. I need chalk. Can you guys see this about right here? Okay, so we have, in a way, it's harder to draw this, so I don't know. But if we have our state space C2, remember I showed that the idea with projective space is that we can imagine the lines through the origin, and that line being identified, or identifying all the points on that line as one equivalence class. So we have something in this which is a line, and we'll call that point alpha beta, or this is the alpha beta line. And if we choose another representation of this equivalence class, we can rescale things. We divide through by beta. This first coordinate is identified with a point in C, so alpha beta is something in C. And so we get like a copy of C for free here. Problems arise when beta is 0, because how do you divide by 0? That's a bit weird. So if we imagine beta being 0 in this second case, this kind of blows up. So we have something like infinity 1, which is not that nice. In a way, we want to capture this as like a finite number. And this is very wrong when I say this, but if you imagine scaling infinity down to 1, then what does that do to the 1? Because we have to divide through. It has to go to 0. I'm happy to explain more about that later, but this is, we can think of this as identifying the vertical line in C2. So we have essentially a copy of C, and that missing point, infinity. And if we look here, we've like wrapped up C, and we've got that one point A, and we've created this compact object here. And that's a long-winded way of saying that when you were doing that quotient earlier, here's what it does. It takes something, an element in SU2, identifies it with its spinner, or normalized spinner, because of that prior bijection we made. And in 1 and 2 cases, it was either identified with alpha on beta, if beta was non-zero, and that was an element of C. And otherwise, it was the point infinity. So that's big. The complex projective line, the projective space of C2, is in a way like a copy of C added this point at infinity. That's what gave us the picture of the sphere. And so now, in a way, we're done. We've got to the sphere from the quotient, and we've landed on our Bloch sphere.
Yeah.
That's a round of applause moment right there. Okay, for the curious, I want to give you the explicit Hopf vibration. I just didn't think it was interesting enough compared to what we did in our Germany arc. So, let me just recap first that the fibers were encoded on the surface of S3, and by quotienting by U1, which was the circle group in a way, we've removed in this surgical manner the fibers of S3, and we've landed on the Bloch sphere, and that gives me happy thoughts. So the Hopf vibration explicitly between the two topological spaces, S3 and S2. I'm just going to breeze through this. It's just this hammer. That could be like a 2-second talk. A little surprise for those who stuck around to the end. I'd like to scan this really quickly.
Oh my god.
LinkedIn.
It takes you to my LinkedIn page. I'm not advertising my LinkedIn, but if you want slides, ask me. Yeah, so thank you. Thank you for coming to my talk. That's it. Okay. Any questions? Questions, please.